So we just finished up our video where we were testing the injectors out of the Doosan Bobcat or the Bobcat Doosan engines, right? And now we're going to move to the high pressure pumps. I've got a high pressure pump here out of a D24, which is our 2.4 liter engines, probably the most common. And I've got one out of a D34, the 3.4 engine, which is used in our larger machines. And the pumps are almost identical in the way they operate. You can see the D34 pump is a lot bigger, has bigger pumping elements, and really the only other difference is the D34 does not have an internal high pressure relief. The D24 has an internal high pressure relief valve, and I think it's somewhere around like 36,000 psi, something like that. So if something was to get blocked or just something happened and this created too much pressure, it has an internal high pressure relief. The D34, since it's not in the body, this is actually a fuel rail out of a D34, it has the high pressure relief in the fuel rail itself. If this high pressure relief was to go bad, fuel would bypass here. This is actually upside down, but fuel would bypass. We actually had a machine we couldn't, or not me, but some guys in our shop were working on that. They could not figure out why they had low rail pressure, and they checked the pump, they checked the injectors, they couldn't figure out, and it turned out this high pressure relief went bad and was allowing fuel to bypass, so it could not build rail pressure. So the high pressure relief is something to be mindful of. Never had a problem with it out of the D24 Delphi pump. But we're not going to tear into the D34 pump since they're so similar. We are going to focus on the D24 pump. Now, we want to properly diagnose these pumps, and that's why I'm doing this video, because these machines are running out of warranty, man. These machines are going to be around forever, just like our old machines with the Kubota engines, that we've been running since the 80s, 90s. To replace a fuel system on those, I can replace a whole fuel system on my 763 for, what, $700? That's a new pump, new injectors, new lift pump, everything. If you misdiagnose, or if you have to buy a high pressure pump for your for the Doosan engine, you're looking at almost $3 grand just for the D24 pump. The D34 pump, we're looking at over $4 grand just for the pump. So we got to be careful. We get low rail pressure, and we can't figure out why we have the low rail pressure, and it's possible that our injectors are just bypassing inside and coming out the return line. But I see it a lot that people condemn this pump when there's really nothing wrong with the pump. They just don't have any other answer. Well, it's got to be the high pressure pump, so they put one on. So how do we diagnose this? How does it work? What does it do? Well, it's kind of a two-stage pump. We have the lift pump here. This actually pulls fuel. This section here is what pulls fuel from our tank through our fuel filter and into the cavity of this pump. And we're going to take all this apart and look at it. And then this charge or primer pump, charge pump, lift pump, whatever you want to call it, charges the cavity, pressurizes this cavity to 86, 87 psi with the vane pump in here, and it maintains that pressure through a low pressure relief on here. And this relief is set to 86, 87 psi. It depends on where you look. Different manuals say 86, some say 87 psi. But how do we start diagnosing this pump? Well, we're going to start with the IMV valve, because if it codes out low rail pressure, it says, check your fuel filter, check your fuel lines, check your IMV valve. Well, how do we check it? Well, using a T25 Torx, we're just going to remove this IMV valve. IMV stands for Inlet Metering Valve. It's what controls the rail pressure. This charged 86 psi goes through this valve, and this valve regulates how much fuel actually goes to the high pressure pistons. You've got a high pressure piston on the top and one on the bottom. So to remove this, we just remove the two bolts using a little T25 Torx and pop it out. And it's controlled electrically, and this is also an electrical, this is the only other electrical connection on here, which is the fuel temperature sensor on this pump. But looking at this IMV valve, you can see we have a screen right here around it. So to troubleshoot this, what they want you to do is, pull this out and check this screen right here. This screen is the last line of defense before fuel gets to the fuel rail and to the injectors. So we're inspecting this screen. We're looking for any type of debris, any metallic looking material, bits of metal, dirt, anything. And if we find anything in here, then we want to go a little deeper into our pump. Now, if I suspect my pump is bad, and I think I'm going to spend $3 grand anyways, I'm definitely going to tear into this thing before I buy a new pump and see if it really is bad or what happened. But how do we check our IMV valve? This IMV valve is what we call normally open, which means when there's no power to this valve, fuel can flow through the screen and out the end here into the pump, into the high pressure side of the pump. This is controlled by system voltage, which is 12, 14 volts DC, but it's controlled via pulse width modulation. It's a signal that comes from the ECU to control where this thing is, how it meters the fuel. Now, it's perfectly acceptable to run 12 volts. We only got 2-wire connection here. You can run 12 volts to here and see if that solenoid will slam shut. You'll hear it. It'll slam shut. When you take away the voltage, it'll slam, it'll spring back open. So with no voltage, this should allow full fuel to flow through it. Now, how do I test an IMV valve? Because just this IMV valve is like $800, $900. They might even be $1,000 now. So we do not want to misdiagnose this piece either. Again, it's perfectly acceptable just to send 12 volts to it and open and close it. That's not a problem. But I like to check it through its full range of motion. So what I've built, I just use a 12 volt Milwaukee battery, and I've got a servo controller or a servo driver and a motor controller. And this is how I test actuators and stuff. And I've got a little pigtail here that I plug into it. And I just want you to see how this works so we kind of know what we're looking at. And let's see, you can't really see inside here. You can't see the valve moving. So I'm just going to use this little stick here. See how that comes up? Comes down. So I'm doing that through the motor controller. There it is. That's a better shot of it. So this is what the ECU is moving to control rail pressure. And see, I can set that at any position I want with this servo controller. If I was to run just 12 volts to it, it would slam shut. There's the shut position right there. There's the wide open position. So that's how I like to test my IMV valves, but with this servo controller, because I can test it through its full range of motion and make sure it is actually working properly before we condemn or misdiagnose an IMV valve. So that's how we test the IMV valve. I did have someone state that they did not know this was normally open, but they weren't getting any rail pressure. They pulled the IMV out and they'd actually discovered that it was stuck in the closed position. So by running that 12 volts on and off, he was able to get it freed up and working again and get his machine going again. And I haven't heard anything since, so I guess it's still operating. So I don't know why it got stuck. I mean, we could, anything's possible, but just know that that's how we test our IMV valve. Okay, so now let's say we found metal shavings on this, or we found debris. Where would it have come from? The most likely possibility is from this vane pump. This vane pump, like I said, is the one that pulls fuel from the from the fuel tank through the fuel filter and into the pump body itself. So to check that, we're just going to pull this outer cover off. Basically, I just want you to see there's no magic to this. There's nothing special. There's nothing to be scared of. Anybody can take these off and open them up. This is just a cover plate here, and this here is our vane pump section. Now we got a little door here. We can just open up. We can pull this outer cover off. We just got a little roll pin here, and now we can see our vanes. Right, 1, 2, 3, 4. If we were to get metal in the system, the most likely cause of that are these vanes here. Either got debris in there or water or rust. It lost its lubricity for some reason. Gasoline. A lot of people put gasoline in these machines, and they take out pumps and injectors faster than anything. But yeah, these veins here will start digging into the body, and that debris will get pushed into the pump and come over to that IMV valve. And a lot of those smaller particles can make it through this screen because it's not a very fine screen, and they get up to the injectors and take the injectors out. So, you know, before we start just replacing injectors, we need to know why those injectors failed. And that's why we're checking all this. Now, to pull this whole vein pump section off, see we got another little back door here that we can take off. That's the inlet and the outlet. The inlet fuel come on there, and the pressure side will come out that side. Just a little better look at how the vein pump is situated. Now, those veins are backed by springs. So if we push this center section out, just be careful before you pull it out to make sure that we have it covered up with something so that you actually catch those springs and veins, because they shoot off, you're done. It's, yeah, good luck finding replacements, you know what I mean? So that's the only thing you really need to be aware of on the vein pump itself, is just be careful not to lose those veins and the springs. So this would be the drive side of that vein pump. Here's the inlet section. Our fuel comes in here, it charges it, goes through here, and when it goes through there, this little piece here is our low pressure relief valve. This is what regulates that 87 psi within the pump body itself. I'll have to take this high pressure side off to show you that, but okay, so it charges here, charges the cavity with 87 psi. That fuel comes over to the IMV. The IMV lets the fuel bypass it into these high pressure pumps here. This is actually the fuel that's going to the fuel rail through this port right here. These two pistons charge that pressure up to, what, 26,000 psi, and out this right here. Let's take a look at these high pressure pistons real quick. And if you'll notice, there's two of them. They're horizontally opposed, like a boxer motor, right? There's just a camshaft in here that's spinning both these pump elements. There is spring pressure behind that, of course. Okay, pull this off. We got a little metal gasket here. Okay, here's what the pump element rides on. So this will be on the crankshaft, camshaft, whatever you want to call it. When that camshaft comes up, squeezes that pump element. See how that works? So as this pump is coming up on the pressure stroke, this pump on the bottom side is coming down on the intake stroke. We have a larger hole and a smaller hole on this pump head. The larger hole is the intake for the fuel, and this smaller hole would be the high pressure fuel coming out. Here's our piston, goes in there. Look how tight those tolerances are. That's, you know, air pressure hardly get through there, and the fuel is the seal, is what seals that in there. But we're talking about very, very tight tolerances in here. So we want to expect, you know, that pump element and inside here as well. Now, in order for it to pull fuel in and push high pressure out, we have a check valve on either side of this pump head. We're not going to take those out, not really necessary. You shouldn't ever have to. You shouldn't ever really have to get this deep into the pump. But like I said, if you're going to replace it, you might as well tear it down and find out what happened, right? That's the best part of I guess learning and figuring this stuff out. But anyways, I've never had a problem with these checks in the actual pump head itself, but it is something to be aware of. And again, when we get to why we time this, it's important to, you know why we've got that horizontal, one piston's coming up, one piston's going down in this motion here. Now that I've got that pump head out of the way, now we can get this low pressure relief valve out. This is all it is. It's a spring and a little valve. Let's see how that works. So When it reaches 87 psi, it pushes against that spring and allows the excess pressure or the excess fuel to bypass, so we can maintain that 87 psi. So low pressure relief valve. Now let's take off this other pumping element. This is the front, this is the engine side, and again, you don't have to pull the front cover off the engine to remove this pump. They're just bolts, 3 bolts from the back side of the pump. Remove those bolts and we can slide this right off, and you'll see the gear here on the front. This pump is also a 1-to-1. What I mean by that, 1 revolution of the engine equals 1 revolution of this fuel pump. That's the way it's geared. Not 2-to-1 or 3-to-1. It's 1-to-1, and that's kind of important to know as well when we get to why we time these. So same exact thing on this side. You know, we've got the piston, pump head, you know, got our checks up here. So exactly the same on this side. You know, this is the piece that rides on our cam again. And it's probably, I don't even know if you're going to be able to see this. There's my metal gasket. But inside there, see, there's a flat spot. I don't know if you can kind of see it oscillating back and forth, but it's moving up and down. And by moving up and down, that's what's pushing that piston and creating that high pressure fuel. Okay. Now, we could take this pump body apart, you know, we've got the bearings and the cam and all in there, but you shouldn't ever really have to go past this point, but it is possible. This is where fuel comes in from the fuel filter. This small nipple up here on top is the return from our injectors. You know, our injector return line manifold comes back to here, and this is actually like a venturi. So as you know, when we're bypassing our low pressure relief here, when we build that 87 psi, that fuel is allowed to return to tank, and that venturi actually pulls a vacuum from the injectors to help evacuate that fuel through the return line. So pretty neat how that works. So hopefully that makes sense on the pump, okay? Like I said, there's not a lot to it. It's very straightforward, very easy. I've seen what looks like rusty water inside here, kind of like muddy water. It's because water has got into this and the inside starts to rust. And once that happens, yeah, we have to condemn the pump. It's a bad pump. We have to send it off and either have it rebuilt or buy a new one. And if that happens, or I guess another way to check for contamination is, you know, we're talking about why our injectors failed, you know, what happened. You know, it's usually contamination. Majority of the time, a fuel system failure is contamination. So looking at the fuel rail here, you'll see on the end of the fuel rail is the fuel rail pressure sensor. Now, what Bobcat wants you to do is remove this sensor. They want you to do a swab test. So I just use these long wooden Q-tips, get on Amazon, Tractor Supply, hell, you can get them anywhere. And we're going to put that into this port, and we're going to just rub it around inside there, and we're going to swab the inside of the rail. We're going to pull it out. And what we're looking for, see how all that dirt and all that rust? Well, that tells me that this fuel rail is contaminated. So we need to replace the fuel rail. We need to replace the fuel lines and probably the injectors. So we probably lost all the injectors with this fuel rail, but this isn't always a telltale. For me, sometimes it's difficult. You know, this one is very dirty, and sometimes it's just difficult to do this test. But I run 5 or 6 of these swabs, you know, through there at different points in the rail and try to get a good idea of what's going on. I mean, usually right where we have to kind of force it through the hole where the sensor is where we pick up a lot of dirt. So we want to make sure we kind of clean that area out and just do it multiple times just to make sure, because these fuel rails are expensive. You can't buy this sensor by itself. If you want to replace this sensor, which I don't know that I've ever seen one of these sensors go bad, but a lot of people want to buy one because they're not building rail pressure and they're like, what the hell, you know, they can't figure it out. They just think they got a bad sensor. Well, you can't buy the sensor without buying the complete rail. The only other thing really to know about this fuel rail is that there is an orifice at each one of these outlet pipes going to the injectors, and that orifice just helps control and smooth the fuel flow to the injectors. And it is possible that debris gets in one of those orifices and clogs those up. So kind of another thing to check, but yeah, it's very rare. As a matter of fact, I've never seen it happen. I've just heard of it happen. Another thing on common rail diesel engines, man, you never crack these lines. There's no need to crack a line on a common rail diesel engine to see if there's fuel coming up there. Number one, if you crack the line, it's recommended you replace the whole line because it's 30,000 psi. Once we clamp that down one time on both sides on the rail and the injector, it kind of forms the line to that. We don't want to take any chances of debris or anything getting in there, so we replace the line. But common rail diesel should prime itself. You have no problem with the air getting through there. You don't have to bleed the injectors. This is an old school mechanical fuel system. Just never crack a line on a common rail diesel engine. You don't have to. You know, if you've got a problem somewhere else, I guarantee you it's not air in the line. Or you don't have to bleed air from the injectors. Okay, so hopefully all that makes sense. Again, I'm just trying to help you diagnose these fuel systems, you know, the best of our ability, because these things are out of warranty now. You know, these machines are going to end up at our, you know, on our dad's farm in our backyard, you know, in another 10 years. And, you know, you take dirty, contaminated fuel out of the barrel back behind your barn and you dump in here, we're gonna contaminate that fuel system, and you're gonna lose injectors, you're gonna lose pump. And if you had to do a whole entire fuel system, and we're upwards of $10,000 just to do a fuel system on these things. So any questions, let me know on all that. Let's talk about why we time this fuel pump when we put it back in. So we pull it out, we put it back in the engine, we need to time that gear. So before we go to the whiteboard, because I need to show you this on the whiteboard, like I said, you got these two pistons are horizontally opposed. When one is on the compression stroke, one is on the intake stroke. They're moving together like this. Okay, and we got two of them. It should be like, yeah, like that. That's better. So this one's making pressure. This top one would be the intake. Now the top one's making pressure. The bottom one's the intake. So only one of these is creating pressure at a time. All right, let me turn you around. Let's take a look at the whiteboard on why that's important. Okay, so before we start on why we time the pump, let's talk about how this injector fires. You know, we did a crude test the other day where we were just firing this thing with a hand pump. This injector has pre-injection and main injection events. So what that means is your piston is, your cylinder piston is coming up on the compression stroke. This will actually do a pre-injection before it hits top dead center, and then there's a main ejection event. So that could be up to 5, even 7 pulses of this injector as that piston's coming up. And in order to achieve that, this thing has to pulse in what we call micro seconds. Now, a microsecond is very difficult to comprehend for me because I'm stupid. But a millisecond, okay, I can comprehend a millisecond. But a microsecond is so fast, it's just unfathomable. Okay? And we want this to fire at the highest pressure possible based on ECU demand pressure. What do I mean by that? Okay. Our ECU has a demand pressure to make horsepower. And that pressure can be anywhere from 5,000 up to 26,000 psi. Okay, I'm going to use a good round number. Let's say 10,000 psi is what our ECU is currently demanding from our fuel pump. Okay. Now, this number is going to be static. It's not going to change. Now, when I was talking about our pumping elements, we have to think of our actual. Now remember, this is demand. This is what the ECU wants to have. Come on, buddy. A in demand. That's 10,000 psi. Okay, I'm just using 10,000 because it's a good round number. So let's think of the actual pump pressure as a frequency. Why do we think of it as a frequency? Because we've got two pumping elements, right? So as that thing is on the compression stroke, what happens? We build pressure up to that demand, and now we're on the intake stroke. Now we're on the pressure stroke. Now we're on the intake stroke. Pressure stroke, intake stroke, pressure stroke, intake, and so on. Now remember, we have two pump elements, right? So while one is on the pressure stroke, the other element is on the intake stroke. Pressure, intake, is the exact opposite of the other piston. Okay, now we want that injector to fire as close to 10,000 psi as possible. So as our cylinder piston is coming up, the injector, the ECU is going to fire the injector at the right time. But what happens if our injection pump is out of time? That piston might not be at the top of this curve. Now we might be firing our injectors right here. If we've got our pump out of time, the ECU is firing the injector at this point. And I don't know what that point is. Maybe it's 9,950 psi. Because it's not at maximum pressure. Because, you know, imagine our fuel rail as a bucket with holes in it, and we're trying to fill it up with water, but water's leaking out. Well, water's leaking out of our injectors and out of our return lines and everything. So our pump is constantly trying to reach that max pressure. And we even see that on the ECU when we're looking at actual pressure versus demand. There's a fluctuation between there. Actual pressure is constantly just fluctuating. That's why we got to think of this as a signal or as a frequency. And we want it at the highest. We want those injectors to fire on the peak. And so hopefully this is making sense. There's a lot more to it since it's a 4-cylinder motor. 1, 2, 3, 4. You know, we're only firing one cylinder at a time. So this piston would fire for number 1. And again, the pump is 1-to-1 with the engine. So as it's turning, as number 2 is going to fire, it's going to be at that peak. Number 3 is going to be at that peak. Number 4 is going to be at that peak. You know, we don't want it firing down here. If you don't time your injection pump, more than likely this 50 psi difference, you're not going to notice a difference. You're not going to feel any difference in horsepower. You're not going to be able to tell because everything is happening so fast. We can't, you know, it's not comprehensible to me anyways, as fast as this is working. But if we're not at maximum demand pressure, we are not at optimum 100% performance. You know, we got this demand pressure because that's what the ECU says. This is the most, this is the best pressure for the most reliability, the cleanest burn, the most horsepower. You know, we want to be firing at that demand pressure, not below it. So, like I said, if you don't time it, you probably won't even notice a difference. But this is why we time the injection pump. Like I said, I really hope that makes sense. And thanks again for watching. I really do appreciate it. Hopefully this helped you out somewhat. I know we rambled on real fast because it's a lot of information to cover, but it should give you the basics on how to kind of troubleshoot, you know, your fuel system a little more and hopefully save you some money in the future. So the only reason I do these videos is for you, to help you. I don't do these for me to help me. You know, I do it the hard way. So just a thumbs up on the video. That's how you help me. That's how I know that these videos are helping you, and I'll keep doing these videos. So thank you so much for watching. Have a wonderful night.